You have learned that the inertial law, such as the Newton's second law, is only valid for the measurement made in the inertial frame. In this case, you have external force acting on the mass A here. Due to the force, the mass experiences the acceleration and change in terms of velocity. Which Newton's second law is valid to describe this activity? For the Newton's second law, we know that F is equal to ma. So in this case, your acceleration must be absolute. For the first equation, the acceleration is measured at point A with respect to O here. So O here, you have the label X, Y, Z in capital. Therefore, this is inertial frame and the frame is fixed and the acceleration measured from O here is absolute. So this equation is valid. Since the acceleration A with respect to O is equal to the acceleration B with respect to O here plus acceleration A with respect to B here, therefore this second equation is valid as well. For the third equation, you have acceleration at point B here with respect to A. So this is the vector. So this is acceleration at point B, but we want the acceleration at point A. So this is wrong. Then we have acceleration at point A with respect to B, which is this vector. Point B is non-inertial frame because you have small letter of x, y, z coordinate. If point B is a rotating frame or translating frame with acceleration, then this equation is not valid because the acceleration measured here is a relative value. This equation is valid if the B is a translating frame with constant velocity or zero acceleration. So in this case, this equation will be valid for a translating frame with zero acceleration. So in this case, it's still considered inertial frame. And the acceleration A with respect to B is absolute. Therefore, this equation can be made valid. So this equation is invalid because you are using the acceleration at point B instead of point A. Lastly, this acceleration is wrong because you have acceleration B/A, not A/B. So you have acceleration B/O, which is this vector, and you have acceleration B/A, which is this vector, which is wrong compared to the graph here. So this is not valid. In more specific, which Newton's second law will be valid when the point B and A are moving? So these 2 points are moving. So which one will be valid? So the answer will be these 2 equations. Because the acceleration that you obtain for the mass A here is absolute value. Which Newton's second law is valid when the translating frame at point B is moving in a constant velocity? So if this is moving in a constant velocity, the acceleration will be equal to 0. So if the acceleration B/O is equal to 0, then this can be simplified into this equation. So this will be valid as well. Which Newton's second law is valid when the translating frame at point B is accelerating? So if it's accelerating, AB/O is no longer equal to 0, then we cannot let this term to be 0. In this case, we cannot use this equation anymore, and we have to use these 2 equations to solve the problem. Bear in your mind, law of inertia can be applied only in the Newtonian reference of frame or the inertial frame. For example, we can only use the Newton's second law, which is F equal to ma, by using absolute acceleration. So these are the 3 equations that follow the Newton's second law. For the first equation, you use the acceleration at point A with respect to O. So you actually measure the acceleration in the inertial frame. So this is absolute. For the second case, you have the AB/O plus AA/B. For this case, the acceleration at point A is measured at point B. Or frame B can be a translating frame which is accelerating, or it can be a rotating frame. If the acceleration is made at the point B, which is moving at constant velocity, so in this case, you still obtain absolute acceleration at point A. This is because translating frame with zero acceleration can be considered as inertial frame. So this is the graphical representation for the Newton's second law, summation F equal to ma. On your left hand side, we draw the free body diagram which describes the resultant of force acting on this body. On the right hand side, you have the kinetic diagram which describes the motion caused by the force. So this is the common procedure to solve the kinetic problem for a particle. First of all, we choose a suitable inertial coordinate system such as the rectangular, normal, tangential, and the polar coordinate. Then we can draw the free body diagram to show all the external force acting on the particle. Then we can draw the kinetic diagram which shows the particle inertial force, which is the ma. From the diagram, you can form the equation of motion, solve the equation, and then you can find the answer. In this example, you have a 10 kg crate travels along the slope here, and at particular moment at this point, the speed is given by 20 meters per second, and you need to determine the normal force exerted by the slope to the crate. Also, what is the acceleration here? Since this is a curvilinear motion, therefore we can use the normal and tangential coordinate. Then we draw the free body diagram here. So in the normal direction, you have a normal force which is labeled by N, which is acting in this direction. And you have the mass of the crate which is acting downward in this direction. If the angle here is given by 56.3 degrees, or you can find it from this equation by taking the tangent angle, it will be equal to your dy over dx. Then you can obtain the angle to be 56.3 at this point. In the normal direction here, this angle is 90 minus with the angle here. And then to find the angle here, we take 90 minus with this, you obtain the angle. Therefore, you obtain the angle here to be 56.3 degrees. Then you can obtain the W cos angle here and W sin angle here. For the kinetic diagram on the right hand side here, so this object is experiencing the normal acceleration and the tangential acceleration. Therefore, we have the kinetic force corresponding to it in these two directions. By consider the normal direction here to be positive in this direction, take the N minus with W cos angle, it will be equal to MAN. By consider the tangential direction here to be positive, so you have W sin angle is equal to MAT. So this is your equation of motion. So the normal force is unknown, then you remain to be N. Weight is 10 kg multiplied with 9.81. The angle is equal to 56.3. So AN, let's remain first. And then you have the mass equal to 10 kg. So this one is unknown yet. The weight is 10 kg multiplied 9.81. The angle is the same, 56.3. The mass is 10. So the tangential acceleration is unknown. We can find the normal acceleration by using this formula. So you need to take the tangential velocity square, which is 20 square, divided by the rho. Rho is the radius of curvature, which can be found by using this formula. So since y is given, you can obtain the dy over dx and d square y over dx square. Substitute x equal to 16 into these two formula, then you can obtain the answer. Then you substitute inside the curvature formula, then you obtain the rho to be 125. 20 squared divided by 125, you obtain the normal acceleration to be 3.2 here. So you have two equations, two unknown. Solve it, you should be able to obtain these two answers. So the normal force is equal to 86.4. How about the acceleration? So you have obtained the normal acceleration and tangential acceleration. You can find the resultant acceleration by using this formula. Substitute the parameter inside, then you should get the acceleration of the crate to be 8.77.